Okay, today we're going to be talking about the average value. And if f is integrable, yes, I kind of fumbled that word a little bit. If I can take the integral on a to b, its average value across an interval is given by this equation. And this is a huge equation. You want to memorize this equation. We're going to be using this a lot, especially when we get into reviewing for the AP. Okay, so from here it's just a matter of doing 1 over 4 minus 0 times by the integral from 0 to 4 of our function, and then make sure you're not forgetting your dx. So I have 1/4 times by my integral, so I have 2x minus 1/3 x to the third, evaluating that from 0 to 4. So I'm going, when I plug in 4 and I evaluate that, I get 8 minus 64 over 3. When I plug in 0, I get 0, so it really doesn't matter. So simplifying that, we get negative 10/3. And notice how I'm doing this all without a calculator. I realize our book is going to say confirm it with a calculator, or use your calculator. I want you guys to be able to also do this without a calculator. Okay, the mean value theorem for definite integrals. Remember, we had the mean value theorem for derivatives, where we said the slope of the tangent line is going to equal the slope of the secant line. Here, what it means is the area of this rectangle. The area of the rectangle on some point is going to equal the area under our curve. Okay, meaning for some point C, there's some point C where the area of this rectangle is going to equal the area under the curve from A to B. So how do I find the area of the rectangle? Well, you have your height, which is f of c. Okay, that's my height. My width is b minus a. That equals the area under the curve. Remember, area under the curve is our integral from a to b of f of x dx. Okay, so I know that there is some point f of c where that is my average value. Okay, that's what this really means. I know that I'm going to have that there's some point C where on my graph where the function is going to actually have the same value as the average value. Okay, so that's what this really means. There's some function value that equals our average value. Okay, that's key. That's super cool. Find the average value of our interval, and then at what points in the interval does it take on the average value. Okay, so average value formula. Integral from 0 to 2 of our function. Don't forget your dx. So we have 1/2 times by 1/3 x to the third, evaluated from 0 to 2. So I have really 1/6 times by 2 to the third minus 2 to the 0. So that's going to be equal to 4/3. So by our mean value theorem for integrals, our function value, there's some x value where our function, which is x squared, is going to equal 4 over 3. Well, if I square root both sides, I'm going to just encounter the positive one, because that's the only one that's on our interval. I have 2 over root 3. Simplifying that radical, we get 2 root 3 over 3. Okay, our next example. And this is something of a challenging example. Okay, but it's one that you're going to find a lot on the AP. So we have a graph of a continuous function as shown here. and from 0 to 8 on our domain, and I have a function, h of x is defined by the integral from 1 to x of f of t dt. We need to find h of 1. So h of 1, you plug in 1 wherever you see an x, 1 to 1 of f of t dt. Well, what's my area under the curve from 1 to 1? That's going to be equal to 0. Now, is h of 0 positive or negative? When I'm finding my area from 1 to 0 of f of t dt, I think about it as I'm going backwards, okay? I have to change that to a negative 0 to 1 of f of t dt. So our area, it's above the x-axis, but because of that negative sign, we are negative. Okay, for what values of h of x, for what values of x is h of x have a maximum? Okay, so remember, h of x has a maximum when h prime of x changes from positive to negative. We change from increasing to decreasing. So what is h prime of this function? H prime of x equals the derivative with respect to x of our integral function, and what is that? That's f of x. So h prime of x is equal to f of x. So when does f of x change from positive to negative? We change from positive to negative right there at x equals 4. All right, at what values of x is h of x a minimum? Remember, h prime of x is equal to f of x. And we have our functions give a minimum when I change from negative to positive. Our graph never changes from negative to positive. But keep in mind that you also have to incorporate the endpoints. Remember when we were finding absolute extrema, we had to incorporate the endpoints. So I have to find h of 0. We said h of 0 was some negative number. And then now I need to find h of 8. So you need to think about h of 8 is the area under the curve from 1 to 8 of our function f of t dt. So I have this positive area because I'm going from 1 to 8. But I have this really big negative area. So what area looks like it's going to be more, even compensating for this little positive piece? This area underneath here, that's going to be essentially a more negative area. So where am I going to have a minimum? I'm going to have a minimum at x equals 8. Now find the coordinates of the points of inflection. That's where h double prime of x or f prime of x changes signs. So where does that change signs? Change from decreasing to increasing. So one of them is x equals 1. Then I change from at, looks like approximately 3. And then again, here at 6. So points of inflection are when the second derivative changes signs, when the first derivative changes from decreasing to increasing and back and forth. Okay, this next example, very similar to the one that we just talked about, but this one talks about a particle. Okay, so we're going to be doing the same thing. I just wanted to talk about it now in relation to a particle. So f of x is a differentiable function whose graph is given, is shown at the picture on the right. The position at any time t is moving along the coordinate axis where its position is given by our integral in meters. And use the graph to answer the following questions. What is the particle's velocity at time t equals 0? So I'm looking for velocity, which is the derivative of position. What's the derivative of that function? Well, that's going to be f of t dt, or no dt, because I've taken my derivative. The dt goes away. So I'm looking essentially for f of 2. F of 2 is 0 meters per second. Keep in mind, I've given you units, so make sure you're giving me units back. Is the acceleration of our particle positive or negative? So I need to look at the second derivative of position, which is the derivative of this function. Is this sign positive or negative? At 2. It's positive because our function is increasing. So we are positive. Okay, what is the particle's position? So I'm looking for s of 2. So I'm looking for the area under my curve from 0 to 2 of f of x dx. Now, I'm looking at the area under my curve from 0 to 2. So I'm looking for the area of this triangle. Okay, and I think this question is a little deceiving because they don't tell you it's a triangle. I would tell you that from 0 to 4, that's a straight line. Okay, but that is actually a triangle. So that's 1/2. My base is 2. My height is -6. So what's my position? My position is -6 meters. Okay, part D. It's the same pieces, I just had a lot of pieces to this. When does the particle pass through the origin? Okay, so basically, when does this area, my position under here, this area was -6. So it passes through the origin. At 2, I'm at -6. Okay, we just talked about that. S of 2, my position at time t equals 2 was -6 meters. But what happens? I start turning around and I start going positive right in here. So this triangle there is going to cancel out that triangle. So basically what we're going to look at is when is the area essentially cancel each other out, and that's at x equals 4. Approximately when is the acceleration equal to 0? Okay, so we look at our second derivative, which is our first derivative of f of t. When does that equal 0? When does our derivative equal 0? The derivative of this function equals 0 when I have a maximum or a minimum, so that's at x equals 5. Okay, when is the particle moving towards the origin? Alright, so what you need to think about is, we've walked you through all of these questions. So remember, at s of 2, my position was a -6 meters. Okay, so I was at -6 meters here. Then remember, the areas started canceling each other out. So I start moving towards my origin. So if you think about it like this on a number line, at time t equals 2, and the number line is your position, I'm over here at -6. Okay, so I start somewhere, I go to -6, and then I turn around and I come back. So at t equals 2, I'm at -6, then my area starts canceling each other out and I start heading back the other direction. So when am I moving towards the origin? I'm moving towards the origin from 2 to 4, because then at 4 I'm at the origin. I was still in the negatives, but I was moving toward the origin. My area, this area here, was canceling out that area there. On which side of the origin is the particle light t equals 6? So then I'm looking for s of 6, which is equal to the area under my curve from 0 to 6 of f of x dx. So what's my area under the curve? Well, we know here those two areas cancel each other out, so I'm at 0 at time t equals 4. Then I start going somewhere positive. So on which side of the origin? On the positive side. I'm going to lie on the positive side of the origin because my area is positive, so I started moving even more in the positive direction. Okay, that's it for today. Please make sure your lesson summary is submitted on time.